8.1 Introducing Confidence Intervals. Now, this section is going to piggyback off of Chapter 7, where we looked at sampling distribution with a sample means and standard deviation. In Chapter 7, we looked at taking pieces of the population to make an educated guess about how close we should be to our population mean by using samples of the population. And the reason for that is because in real life math, real life situations, I should say, you're going to have some data sets that are extremely large. And it's going to be almost impossible for you to get a population mean. So you can gather up samples and you can use that sample mean and allow a little bit of sampling error and make an educated guess of the confidence interval in which your population mean should be in between. Okay? So I want to introduce confidence intervals by looking at our first example. Now, our first example is on the prices of new mobile homes. And we know that mobile homes are manufactured by the thousands, if not more, yearly. So to give an educated guess of the actual population mean of the price of mobile homes would be almost impossible. So here we have 36 prices listed in this chart. So it says you have a simple random sample of 36 new mobile homes, and those are their prices in thousands of dollars shown in the table. So 63.8 will represent 63,800. 52.5 will represent 52,500. So it says use this data to estimate the population mean of all new mobile homes. Now, what you're getting ready to do is really give a sample mean, but we call this the point estimate. Point estimate. It is the same as the mean of your sample, but you'll hear us use the term population mean, but what we're looking for is to see how close or what range would our population mean fall. So first thing you're going to do is get the mean of the sample of the 36 mobile homes. So you're going to add up all 36 prices. When you do that, you should get 2134 evenly. 2134, and you're going to divide that by 36. And that should give you 59.27, and the 7 is repeating. So we're going to round to 59.28. And this is money, so that's mainly why I'm doing 2 decimal places. Normally when we were doing mean earlier in the semester, we would do 1 decimal. And I did mention if we're dealing with money, we do 2 decimals. So that would be 59.28 would be our actual mean for the 36 mobile homes. Now, if you look down here where it says introducing confidence intervals, it says consider again the problem of estimating the population mean of the price of all new mobile homes by using the sample data provided. Let's assume that the population standard deviation of all such prices is 7.2 thousand. That is 7,200. They want you to obtain the sample standard deviation. Now, there is a whole different formula for finding the sample standard deviation. The formula, we know that is our baby sigma. It is take the population standard deviation and divide it by the square root of n, and that's little n. Now, in chapter 7, we had big N and little n. Now in chapter 8, we're back to just little n. There's not going to be a big N. So little n will represent your sample size. How many numbers is in your sample? So we know that the population standard deviation is 7.2. And we know that our sample is 36 mobile homes. So you would divide 7.2 by 6, because the square root of 36 is 6, and you would get 1.2. So our sample standard deviation is 1.2 thousand. Now, number 3 is the actual question. This is what we're going to be seeing in chapter 8. It says, use the sample data to find a 95.44% confidence interval for the population mean. That is an interval of numbers that we can be 95.44% confident contains you. Now, I want to switch screens right quick. Now, bringing the bell back up, and you do have a new table. It's 2 pages for chapter 8. And this table is going to represent certain percentages that we're going to use in this section. What I mean by certain percentages, if you look at that number 3, it specifically asks for 95.44% confidence interval, okay? Now, the normal percentages that we use are 90, 95, and 99. On the normal bell curve, normal distribution bell curve, to show you where 95.44 comes from, because it's not necessarily spelled out on the table that you have. When you're looking at the portion between mean and z that would be shaded, if we were shading from one z-score, to -1, this would represent 68.3% shaded. That's what this would represent. From one z-score to -1, or -1 to 1, that represents 68.3% shaded. Okay? Let me erase. If we go from -2 to +2 as z-scores, this represents 95.4% shaded, and these are rounded to 1 decimal place, okay? So this represents 95.4% shaded. So this would be from -2 to 2 as far as my shade is on my bell. So what you need to know is that if I'm giving you these 3 percentages specifically, 68.3, then the corresponding z-score would be 1. If I ask you about 95.4% shaded, the corresponding z-score would be 2. And obviously, if I ask you about 99.7, that's nearly the whole bell shaded. We're talking about from -3 all the way to +3. That is literally your whole Bayes. Then that corresponding z-score is 3. Okay, so those are specific special percentages. Okay, now your table is going to consist of z-scores, but they are not from 1 to 1 or from 2 to 2 or 3 to 3. They're going to represent certain different areas of this Bayes. So that's the reason why you have a chart for it. So you might want to write down that one z-score equals 68.3%. Two z-scores represent 95.4%. And 3 z-scores represent 99.7%. And I'll explain this better as we go. But I want to point out those special percentages of the shade on our bell curve. Now, if we go back to our problem, it's asking you to use the data to find a 95.44% confidence interval for our population mean. And so, here is the formula for confidence intervals. All right, we have X bar, we know that stands for sample mean, plus or minus a z-score. Okay, now it has alpha divided by 2. That's going to represent the certain percentage. Okay, I just showed you 3 on our Bayes. That's going to be a z-score that we're going to get off of our table. Times, this formula should be familiar with what I did on number 2. That is our sample standard deviation formula. So that's going to be the population standard deviation divided by the square root of n. So let's take our information that we gathered from number 1 and number 2, and let's plug it into this formula. We know that the sample mean is 59.28. So I'm going to plug that in. Plus or minus, we need a z-score that represents 95.44% shaded. That's why I showed this Bayes. The z-score that goes for 95.4% would be 2. Times, going back to number 1, number 2, we found the sample standard deviation to be 1.2. So we've plugged it in. So we're going to multiply 2 times 1.2 first, and that would give us 2.4. Then we're going to add and subtract from 59.28. So if you subtract 2.4 from 59.28, you would get 56.88. If you add 2.4 to 59.28, you'll get 61.68. So our confidence interval would be from 56.88 to 61.68. Now, what you just found was the range that our population mean should fall based upon a 95.44% confidence interval. So let's put this back into into our terminology. We were looking at prices of mobile homes. So what this is telling me is that my population price, my mean price, should fall anywhere between $56,880 to $61,680. The mean should fall somewhere in between. So there's a specific statement that you need to be aware of making. When we're dealing with confidence intervals, we make a statement such as, we can be 95.44% confident that the mean price of all new mobile homes is somewhere between $56,880 and $61,680. Let's look at our next example. All right, we have the civilian labor force. So you have a chart here, and it says the U.S. Bureau of Labor Statistics collects information on the ages of people in the civilian labor force and publishes the results. 50 people in the civilian labor force are randomly selected. Their ages are displayed below. Find a 95% confidence interval for the mean age of all people in the civilian labor force. Assume that the population standard deviation of the ages is 12.1 years. Then find a 90% confidence interval for the mean age. Now, let's talk about our chart. Let's look at our table. Let's do some labeling on it before I actually get into this example. Now, your chart is 2 pages, which is really within a front and back. And I need you to look at the back. And you know it's the back because if you look at the first column, your numbers should start with 50 going to 2000. That's the back sheet. And there's a little box at the very end of the big chart. That little box, I need you to label it as population standard deviation is known. Okay? Population standard deviation is known. And that's going to go with this little box. And what that means is the wording, the word problem that I give you has to specifically say this is the population standard deviation. If it says that, then you're using the little chart. I call it the little box. If it does not say population standard deviation, then you're going to use the big chart, and that's the chart that is above the box, okay? So we need to label this little chart, this little box, for your percentages, okay? So you will know what z-score to use for when. Now, if you look at the box, your box has 2 rows. The top row is the actual z-scores, okay? This top row are your z-scores, okay? The bottom are the percent subs in decimals, okay? So that whole bottom subscript number deals with that alpha 2 that was on the formula. If you remember when I wrote that formula, I did the z-score and I put alpha 2. That subscript on those Z's represent it. So I'm not going to go into the whole spiel on how to find that. I'm going to go ahead and help you label your little box so you'll know exactly what z-score to pull based upon the percent. Okay? So let's do that. Let's label. The very first z-score, which is 1.282, would represent 80%. So you won't get confused. So I just put lines to separate. The next z-score, which is 1.645, it represents 90%. The next z-score, 1.960, represents 95%. 2.326 represents 98%. And 2.576, the last one, represents 99%. So in green, I labeled the percents that we use all the time. We really don't use the 80% or the 98%. We will use 90, 95, and 99 a lot. So I have those labeled for you. Okay? So I'm going to bag up to the problem. And it wants us to first find a 95% confidence interval. All right? So keep that in mind. We're doing 95% confidence interval. Now, the very first thing you need to come up with is you're going to need that mean. I need to know what's the mean of these 50 ages. Okay? 50 people's ages. So you would add them up and we would divide by 50. So when you add them up, you should get 1819, and we divide that by 50, and that would give us 36.38. And on the first example, we were dealing with money. This is not money, this is ages. So let's round 1 decimal, okay? Kind of let that be your go-to for your mean. So this will be 36.4. That's our sample mean of these 50 people's ages. 36.4. Now, in the reading, they told us that the population standard deviation is 12.1. So they specifically told you, you know your population standard deviation. They've given it to you. So we're going to use that little box. So back, I'm going to give you that formula again. We're going to take the sample mean plus or minus our z-score times the population standard deviation divided by the square root of n. So let's plug in these numbers. Our mean we have is 36.4 plus or minus that z-score If we go back and look at this table, our table here, our little box, for 95%, that z-score is 1.960. 1.960 times the population standard deviation they told us is 12.1 divided by the square root of 50, because it's 50 people's ages in that chart, in that box. So that's our plug-in. Now, when I go to multiply, I keep all my numbers, all right? So I'm going to do the division first. I'm going to do 12.1 divided by the square root of 50. And that would give me, and I'm going to write it all down for you, 1.7111 9841. That's what I get when I divide. And I'm going to multiply that number by my z-score of 1.960. So it still should be in your calculator, times 1.960. That would give us 3.353948885. That's where my number stops. That we're going to plus or minus to 36.4. Now, I do not round. I know this might be a pain, but do not round. Because if you round this number, you're going to cut off your accuracy. So you want it to be as close as possible. So do not round till we get to the very end. So type, I still have it in my calculator. So I'm going to subtract that number from 36.4. And that would give 33.04605112. And I'm going to take that same number, 3.353948885, and add it to 36.4. And that would give us 39.75394.889. Okay? So now, at this point, because I'm at the end, I will round one decimal. Okay? We're going to round one decimal. We're going to keep it the same like our mean. We rounded our mean one decimal. We're going to round our interval to one decimal. So I'm going to write that up here so you can see it. We have 33.0. That 4 doesn't do any changes to 0, but you must write that 0 because that's not 33 on the dot. That's got a decimal point. So put that 0 to 39 point. That 5 makes that 7 become an 8. And that would be my interval. 33.0 to 39.8. Okay. Now, I want to go ahead and bring out what we have here. This number is our sampling error, or better known as our margin of error. Okay? Margin of error, that's really what we call it, but that's our error. I'm allowing myself to have 3.35 rounded of error to my mean of 36.4. So if we take this back to what we did in chapter 7, you were given, with the basketball player's height, you were given 1 inch of error. So that means we went up 1 inch and down 1 inch from our mean of 80. If you remember, the mean we used was 80. So the interval that we were looking at was between 79 and 81. This is the same concept. My actual margin of error, by doing a little math, by taking the z-score and the sample standard deviation formula, it will produce my margin of error. So this margin of error is 3.35 rounded. Okay, some more decimals, but that's around about the margin of error given. So that's how you're coming up with an interval of 33.0 to 39.8. So that means the age, if I'm doing a 95% confidence interval, should fall somewhere between 33 years old and 39.8 years old. Okay, that's what you're looking at. That the mean age for all the people in the civilian labor force would fall somewhere between those two numbers. Now I'm going to do a little erasing so I can do the second part of this problem, which asks for the 90%. So that one was 95. Now let's do 90%. And I'm going to write the formula back. So our mean doesn't change. Our population standard deviation doesn't change. Our little n doesn't change. The thing that's going to change when I go to 90% is your z-score. Okay? So let's plug in our numbers. We have 36.4 plus or minus, and I'm going to go to my little box, and 90%, that z-score is 1.645. Times 12.1 divided by the square root of 50. So again, 12.1 divided by the square root of 50, you would have that same 1.71119841 number, but this time you're going to multiply it by 1.645. And like I said, this changes because now we are doing 90%. Okay? We're doing this one, the 90%. So it's in my calculator, times 1.645. And that would give us a margin of error of 2.814921385 that we're going to add and subtract from 36.4. So when I subtract it from 36.4, we get 33.58507861. And when I take that number and add it, to 36.4, we get 39.2149239. So again, we're going to do one number behind the decimal. So that would give us 33.6 to 39.2 as my interval. And this is with 90%. Now, you do need to be in practice of knowing that phrase for writing the interpretation if it's asked. That phrase would be, and I didn't do it for the 95, but you would change the percent in my interval range. But this is what your phrase would be for 90%. You would say that we can be 90% confident that and we always can come back where it says find the mean, that the mean age, Now, if you want to write all of that, of all people in the civilian labor force, that's fine. But you can just say the mean age is somewhere between 33.6 years and 39.2 years of age. Okay. Next example. Now, the next sheet you should have, it should say 8.2 confidence intervals. And all of this, 8.1, 8.2, kind of is the same running stuff. So I'm doing it all together. But my next example 1, what it says on here, would be medical marijuana. Okay? So if we were to read this, it says an issue with legalization of medical marijuana is diversion, the process in which medical marijuana prescribed for one person is given, traded, or sold to someone who is not registered for medical marijuana use. Researchers studied the issue of diversion in the article Medical Marijuana Use Among Adolescents in Substance Abuse Treatment. The mean number of days that 120 adolescents in substance abuse treatment used medical marijuana in the last 6 months was 102.72. Assume the population standard deviation is 32 days. So A tells us find a 95% confidence interval for the mean number of days of the diverted medical marijuana use in the last 6 months of all adolescents in substance abuse treatment. So this is going to be on the number of days. So we were told that the mean number of days, kind of highlight what we need here, is 102.72, okay? And it also tells me that my population standard deviation is 32 days. So on A, we're going to do a 95% confidence interval on the number of days. So let's plug in. We're going to say, and I'll write the formula again. Okay, so we have 102.72 plus or minus our z-score for 95, went too far, is 1.960 times our population standard deviation is 32 days divided by, and I didn't highlight this for you, how many adolescents, the mean number of days that 120 adolescents, okay? That would be our N. So we're going to first do 32 divided by the square root of 120, and that would give us 2.921186,973 that I'm going to multiply 1.960 by. Which would give us 5.72, 55, 26, 46, 8. That's our margin of error that we're going to add and subtract from 102.72. And since my mean is 2 decimals, I'm going to do my interval in 2 decimals. So I'm going to subtract that number from 102.72, and I get 96.99, and there's a 4 behind it, so it will stay 99. I'll take that same margin of error of 5.72, 55, 26, 46, 8, and add it to 102.72, and you should get 108.445. So that 5 will make that second 4 be a 5. So round it correctly, 2 decimal places, you will get the interval from 96.99 to 108.45. And that would be days. And the next one, same information, we're just switching up our percentage. Our percentage on B says 90% confidence interval. So again, the only things that's changing would be my z-score. So I'm going to rewrite the formula for you. So when we plug in, we still have that same mean of 102.72 plus or minus. And so this time it says 90%. So 90% is 1.645 according to our chart. The population standard deviation is still 32, and our number of adolescents is still 120. So you still would have, when you take 32 divided by the square root of 120, you still would get that 2.92, 11, 86, 97, 3. But this time, you're going to multiply it by 1.645. And we get a margin of error of 4.80, five 3, 5 2, 5 7 1. That we're going to add and subtract from 102.72. So when I subtract that from 102.72, I get 97 point, and we're doing 2 decimals here, 91, because that 4 makes the 1 stay a 1. And when I take 102.72 and add that margin of error of 4.8053 52571, you get 107.53, because that 2, that's 525, and that 5 makes that 2 go to a 3. So that would be my confidence interval. Still days, but that's for 90%. Let's look at the next example. Next example is American alligators. It says multi-sensor data loggers were attached to free-ranging American alligators in a study conducted for the article Behavior of American Alligators Monitored by Multi-Sensor Data Loggers. The mean duration for a sample of 68 dives was 338.0 seconds. Assume the population standard deviation is 100 seconds. A says find a 95% confidence interval for the mean duration of an American alligator dive. All right. So we know we're dealing with a sample of 68 dives, and the mean of those dives would be 338 seconds. And it tells you that the population standard deviation is 100 seconds. So on A, we're doing a 95% confidence interval. So let's plug in. Given the formula, we know that our mean is 338. And we're going to do one decimal, but it's a 0. I'll write it, but you don't have to type it in your calculator. Plus or minus. Now, for 95%, if you need to see it again, our z-score is 1.960. Times the population standard deviation is 100 divided by the square root of 68. That's how many dives. So we're going to say 100 divided by the square root of 68, and that would give us 12.12678.125 that we're going to multiply by 1.960. And that would give us an error of 23.76849125 that we're going to add and subtract from 338. When we subtract, you get 314. If we do one decimal, 0.2. The 3 behind that 2 makes 2 stay at 2. And we're going to take 338 and add 23 point and that decimal. And that would give us 361 point. Now that 6 will make 7 round to an 8. So your confidence interval would be from 314.2 to 368.8. Now, I didn't say this, but I hope you do know you always write the smaller number first. And you notice I use the words TO2. Don't do a dash. Use the words to. And then your bigger number. That's for 95%. On part B, we're going to use the same information. We're just going to change our z-score to match 99%. So, putting that formula back down here. Plugging it in. 338 plus or minus our chart. 99% is 2.576. That represents 99%. Same population standard deviation is 100, and same number of dives is 68. So when you divide first, you still get that 12.12678125. And I'm going to multiply it this time by 2.576. And that would give us a margin of error to be 31.23858885. Then we're going to add and subtract from 338. So when I take that number and subtract it from 338, and we're going to do one decimal, so I get 306.8. And when I add, I'm going to get 369.2. So for 99%, you should be between 306.8 to 369.2. And I didn't say that, but this would be what? Seconds. All of this is seconds. Just in case you wanted it to make sense to you. And this will be the last example for 8.1 and 8.2.